So the second derivative test is a little, it can work alongside the first derivative, but what it's able to do is if you have a critical number and you plug it into the second derivative, it'll tell you right away whether or not it's a maximum or a minimum. So you don't really have to test around the critical. It'll tell you right away, yes, max, min. So second derivative is cool and a little bit better, but only if it's easy to find the second derivative. Because as you all will know, sometimes finding a derivative is a real pain. So finding a second one would be could be quite difficult. So it depends, right? Depends on the function we're given, whether or not it's worth it. So let me show you the technique and then we'll go from there. So let's start with something really easy. It's number 1 on your homework. So this is a parabola, right? And we know that it's opening upward, right? So it tells you, so it starts off asking you stuff like concave up, concave down. So let's go ahead and graph that guy. It was x squared minus 2x plus 8. Oh man, this, I just realized my keyboard broken. Let me switch to my laptop keyboard. The X button and the space don't work. It's kind of funny. Okay. Minus, what did I say, 6x? I already forgot. Minus 2x plus 8. Okay. All right. So we can see that this is a minimum, right? You all agree with this?
Yes.
And then we can see that we're decreasing over here and increasing over there. So we took a first derivative. If we plugged in any number over here, the first derivative would be negative. If we plugged in any number over here, the derivative would be positive. So if you find a second derivative, this number will be positive, which means concave up. So when the homework and the book, when you read the theory, concave up means that it's opening upward. So concave down would be opening downward. Okay, that's all they're saying. That's all that means.
And, you said that's only if the second derivative is positive is when.
Yeah, exactly. So let me give you this next example so you can see a better one here. Example 2. So let's rehash this one more time. So they gave us this function. Concave up means it's opening upward. And of course, we saw the picture. It was opening up everywhere, right? It's never changes. It doesn't all of a sudden flip downward. So yeah, everywhere it's concave up. That's why concave down is D and E, because there is no place on the graph that it starts to go downward. So number 2, I think will make more sense. So let's do that guy. Okay. Oh, God, I keep using the broken keyboard. Gx equals 6x squared minus x cubed. 6x squared minus x cubed. So this is what I want you to see. Before we start solving things, I want you to see the theory first, just in case you didn't read the book. So you see how right here we're opening upward, right? Before the number 4, right, of this section. So we are concave up from negative infinity all the way till here. After this point, we're concave down. See what I'm saying? So concave down here, concave up there, it looks like. So let's look at the answers here. So concave upward, negative infinity to 2, negative infinity to 2, which is actually here. So yeah, I was a little off when I said that right there. So biscuits. Let me just go ahead and plug that number in. Keep using the Rogan keyboard. That was 6. Is it not 6? It was 16. Okay, so it turns out, which we'll show you the work as to how we know this, right? It's just a moment. So from negative infinity all the way until here, we are concave up. After this point, we begin to become concave down. So this is like a upside down parabola. After here though, before here, we're concave up. So the question becomes, okay, where is the cutoff point, right? Where do we know that it changed concavity? Okay, so how do I know where to cut it off? So that's when the second derivative will come in handy, okay? So let's do problem 2. Do you have any questions on that basic idea so far before we start? Okay. So concavity again just means if it's opening upward or downward. And where do we decide it's no longer up or down? That is up to a point of inflection, which is found with the second derivative. Okay, so let's do this first example right here and explain it. Determine the open intervals on which the graph is concave downward. Or upward. Here's the function they gave us, which we graphed earlier. So we know what it looks like. Okay. So first thing you do is take 2 derivatives. So first derivative will be 12x minus 3x squared. Second will be 12 minus 12x, right? No, 6, sorry. Okay. One moment. Any questions on the derivative? Is that okay?
So you did the derivative twice since it was asking you to find the second derivative, right? Correct.
Well, I did it twice because we're going to use both of them
Okay.
to find out what's happening with concavity, critical numbers, maximums, all that stuff. So we need
Okay.
both of these guys.
Gotcha.
So remember, just to remind you, this tells us, oh man, I wrote that all stupid. Let's make a note. This tells us about increasing / decreasing. This tells us about concavity and inflection points. The quick note, inflection point is a point where we have a change in concavity. That's all that means. Okay, so remember how we said setting the derivative to 0 gives us critical numbers, right? That's what we did last time. So we would solve for x. So let's see here. Factor my 3x out of both of these guys. That's gonna be 4 minus x equal to 0. So we set 3x equal to 0, 4 minus x equal to 0. X is 0, x is 4. 4, yeah. Because well, these are critical numbers, right? So now we will set the second derivative to 0, which was 12 minus 6x. So that's going to be factor your 6. 2 minus x equals 0. So x equals 2. This right here is inflection point, or a point of inflection, however you want to read that. Okay. Slow it down a second. Okay, there we go. That's better. Okay, you guys still with me? Do you see that how we found the critical numbers, and now we're doing inflection, right?
Yes, sir.
Okay, so this is the point where it will change in concavity. These are the points where we'll have local minimums or maximums. Okay, so sometimes they can be the same, but not always. Okay, so let's get back to the question, because I already forgot what it was saying. It wants to know, oh, yeah, it's up there. Open the intervals where we are concave down or up. So if the second derivative is negative, so let me write you a note here. If the second derivative is, well, first let me write this note, is equal to 0 at some x equal to c, then c is an inflection point. If the second derivative is positive, then the graph is concave up. This implies minimums at critical numbers. If the second derivative is negative, then the graph is concave down. This implies max at crits. No, shorten up there, critical numbers. So now let's look at the picture. I'll leave this up for a second. Oops. Drop my binder. Here's the graph. So we had critical numbers at 0 and 4, right? So there it is, 0 and 4. We had a change in concavity at 2, right? So you can kind of see how this is going to work. So we are concave up at 0, which means we have a local minimum. Concave down at 4, which is a local max, which we'll calculate in just a moment. And then we change from concave up at this point. Any questions about this theory so far? Okay, so now let's test for max or minimum. So remember, just a heads up, you can you don't do both. You either do the first derivative test or the second derivative test. If you're doing maximums or minimums, you don't have to do both. You know how before we tested around these points to figure out what's going on? You can use this guy to just find out straight up what's happening in 0, what's happening at 4. I don't have to test around it. Well, let's do that. Okay, so critical numbers were x equals to, we said 2, no, 0 and 4, right? Already forgot. Yeah. So use second derivative test. So I'm just doing extra work here just so you can see how it all works to determine maximum / minimum. So the second derivative at 0 would be equal to, second derivative is going to be 12 minus 6, right? 6x. Second derivative at 4 will be 12 minus 6 times 4. So negative 12. So this implies concave up. So minimum at x equals 0. Concave down. So maximum at x equals 4. But to answer the original question, because I feel like I got a little off topic, but I'm trying to show you where we're going. This is the whole point of the second derivative. find out maximum minimums. That's one thing it can do. But if we use the point of inflection, right? What was the point of inflection?
To see where the point stops before it goes to the other side, right? Where it's like up or down.
Yeah, exactly. And we found it to be,
Yeah, because you're looking at the graph and you were saying how we might wonder when is that point that it stops where it's considered to go to the other part.
yeah, exactly. Because like
Okay.
we're, when are we going up or down, right? So
Right.
at 2 was that special point. Inflection. So before that, we were concave up, concave down. And then we had criticals at 0 and 4. So to answer the original question of the homework, concave up, we would say from negative infinity all the way until 2. Concave down all the way from 2 to infinity. And if they were to ask, minimum would be at 0, comma something. Max would be at 4, comma something. That's 0. According to the graph, this is 0 and 32. Okay, so I did extra work on that question, even though the answer is something simple. I just want you to see what it can do. Is there any questions on any of those steps?
I was just wondering about how we knew that it was 2, because I know we did the work, but why was it 2?
So inflections point happens. Look at this again here. So it happens at a point of inflection,
Right.
which is when the second derivative is equal to 0. So what number makes it 0? That's gonna be 2. So you solve for it.
Oh, okay, because the other side wasn't able to equal 0 necessarily.
Yeah, you find the second derivative and set it to 0, and then you solve for x. That's all you got to do. And then the first derivative set to 0 gives you critical numbers. So these do different things.
Okay. Will that always be the case every time where the first is different than the second?
The first and second do different things, but sometimes these x's could be the same.
Okay.
So there's possible that you'll have a critical number that turns out to be an inflection point and not a max or a min. That does happen. Like I think something like this would have one. Stupid keyboard. So you see how this point is if you find the derivative of x cubed, you're gonna get 2x squared, right? You set it to 0, the 0 would be 0. So 0 is a critical number, but it's also an inflection point because it's concave down up to here and then suddenly concave up from here. So this is an inflection point and a critical number, but it is not a max or a min. It could be a local maybe, but anyway. Any questions on number 1?
So is it equal to 0 because we said it equal to 0, or sorry, I'm just having trouble.
Yeah, we're
understanding this one.
choosing.
Okay, okay.
Yeah, so, okay. If you want to hear the theory, right, let's look at this. We choose to set the derivative to 0 to find these special critical numbers because the derivative has slopes of 0 here. Remember how back in chapter 3 and 2, we talked about the derivative as slopes of tangent lines, right?
Yeah.
See how the slopes are increasing and then suddenly at the peak, the slope is 0.
Mhm.
So that's why we set it to 0, because we know it happens at local maximums or minimums.
Okay.
Same thing with the inflection point. So we choose it for a reason. And when we solve it, we have the x values we need. All right, so let's move on to a question that actually asks for maximums and minimums. So I don't think that happens until actually till the very end. So let's do an easy one where we just answer the basic question. Let's do that first. Number 3. Because I know I did a lot of stuff on that question there. So example 2, problem 3. So we will just figure out where we are concave down and up. Right? So they give us a function. First derivative. Second derivative. We set this one, we need to find out where we're concave up and down. So all we got to use is this guy. So set this to 0. So factor in -6, we get x plus 1 equal to 0. So x is equal to -1. Oops. That should be minus. This is going to be plus. Okay, so x equals 1.
Sir, can you move it a little bit? I think the light's kind of,
Yeah, I'm trying to get out of the light there.
I think that's good.
There we go.
Thank you.
Okay, so this is the inflection point. So to just answer the question, you could say we were concave. Well, we will treat it similar to the first derivative in the last section. So I'm not going to do anything fancy like I did earlier. So here's a special point. So test something over here, test point, something over here, test point. So second derivative at 0 is equal to -6 times 0 plus 6, which is 6. Second derivative at 2 is going to be -6 times 2 plus 6, which is -12 plus 6, which is -6. So we are positive, negative. So the answer will be concave up from -infinity all the way until the point of inflection. That's the cutoff point. Concave down 1 till infinity to start right after. That's it. And this is your answer. So we don't have to do all that other stuff, at least not yet. But I wanted to at least try it once real quick. And that's what they got. Okay, you guys cool on number, so that's what they were asking for example 1, but let's do number 10. This has multiple points of inflection. Excuse me. He says, given, I'm going to try to phrase it better. F of x equal to 1/2 x to the 4th plus 2x cubed. Part A is find the points or point of inflections. So we got to find the second derivative in order to do so. So it'll be 1/2 times 4 x cubed plus 6x squared, which is 2x cubed plus 6x squared. Second derivative will be 6x squared plus 12x. So you set this guy to 0. Again, I'll write you a note. To find the inflection points, set f double prime to 0. So this is set to 0 on purpose. So factor, that gives us x plus 2. So x equals 0, x equals -2. So this has 2 points of inflection. Let me double check. Subtract 1, 2, subtract 1, do it again. Yeah. So they want to know what the actual point is. We only have the x values. So to answer their question, you have to go and find 0. Right? So that'll be -1 plus or -4, which is -5. So part A answer will be this. 0, 0, and -2, -5. Did I do that right? This is supposed to be squared, hasn't it? Here. Cubed. I'm sorry. Yeah, that should be into the original, not the derivative. Fourth. Let me fix this. So to -2 to the 4th power, that's going to be 16 times a half, which is a +8. -2 cubed is -8 times 2 is a -16. There we go. So it's -8. Because to find the actual point or the location, you need to use the original f, not derivative. So here's the answer for part A. That's what they got here. So the smaller inflection is -2, -8. So that's what we got. 0, 0. Now we're going to figure out where do we concave up and down. So similar to, so part B, find out where we are concave up / concave down. So you do the same thing. Plug in your inflection points. So here's 0 and here is 2. Oops, let's make this 2, this -2. Okay. So we plug in numbers in between to figure out where we're concave up or down. So into the second derivative. So I'm going to choose a test point of -3, test point of 1. 1, actually, this is -1. Because we're below 0. So I'm testing around these points because these are points of inflection, meaning we have a change in concavity here and there. All right, these are the special points here. The second derivative at -3 will be 6 times -3 squared plus 12 times -3. So that'll be 9 times 6, that's 54, right? Minus -3 times 12, that's what? 36. Is that right? That's going to be positive. That's all that really matters. Second derivative at -1 will be 6 times -1 squared plus 12 times -1. That's going to be 6 minus 12. So that's going to be negative. The number doesn't matter, just the sign. But we can write it if you want. Now let's plug in the 1. That will be 6 times 1 plus 12 times 1. So that's positive. So to answer the question, concave up, you would say this section and this section. So -infinity all the way until -1. I'm sorry, -2. That's the inflection point. Union. -1. No. 0, sorry. Till infinity. concave down at -2 to 0. So here are the answers. For part B. Yeah, give you 1 second to write that. I'll be right back. Okay. Here we go. So the original function was f of x equal to, oops. One half x to the fourth plus 2x cubed. Okay, so this is what I want you to see. So we have those special points, right, of points of inflection were 0, 0, right? And -2, -8. So from here to there, suddenly we change concavity. Then we're opening downward and suddenly we're opening upward. That's what's happening. So we had two different changes in concavity. So we had three intervals of, we had to combine for, or two intervals to combine into for upward and one for the downward, the little in between. Looks like that's what they got here. Alrighty, now let's do where they actually asked for it. 14 says find all relative extrema, meaning maximum, minimum, and they want us to use the second derivative test. All right, so you guys cool on this one, right? Find all relative extrema. Okay, so what we're gonna do is what we did in the first example. We're gonna find all the critical numbers and plug them into the second derivative and then determine, is that a max or is it a minimum? Okay, so first derivative is 4x cubed minus 12x squared. Second derivative, that will be 12x squared minus 24x. All right, so set that to 0. Factor your x squared. That gives us x minus 3. Right, factor this guy, yeah. So x equals 0, x equals 3. So those are my criticals. So we may have max or min, or maybe both. Okay, set this guy to 0 to find the inflection point, just in case we need it. Alrighty. So notice how we have x equal to 0 here and here, right? So it looks like this one may not be a max or a minimum. This one probably still is. But let's go ahead and graph it just so you can have a good idea what's happening. Okay, so we have 0, we said was a interesting number. 3 was a critical number. Okay. Oops. So here we have a point of inflection. You see that how it's concave up and then down. But over here, it's an actual local minimum. So if I were to plug this into the second derivative, I'm going to get 0 because it's not a local max or a local minimum. So that's why it's not going to work. So let's say I didn't know that, which maybe that doesn't make sense. But plug in both of the criticals into the second derivative. Let me write that better. Zero. So it's not positive or negative. So I don't know. It's not a max or a min. Plug in the 3. That gives you what, 12 times 9 minus 24 times 3. What's that going to be? It's 108, right? 24 times 3 will be 72. So 108 minus 72, 36. So that, anyway, none of that mattered, right? If it is positive, since, let me put this in English, since the second derivative is positive at x equals 3, then it is concave up. Therefore, it is a minimum. So the minimum is right here at 3. But we need the actual X value. So the next thing you have to do is plug in the 3 into the original. So 3 times 3 is 9, times 3 is 27, times 3 is the 81. That's going to be negative 20. So final answer. So minimum at 3 comma negative 20. Which we could see on the graph, right? But what I did to determine this was use the second derivative test. So there was no max because we could tell from the graph. And we tested both critical numbers. One was 0, which means inflection. One was positive, which means concave up, which implies a minimum. Are there any questions about example 4? That's pretty much it for this section. You guys have any homework problems you wanted to work on? Anything you're struggling with?
No, but can you open up 4.3 and 4.4 on Canvas?
Oh yeah, I don't know they closed. Let me do that for you. Sorry about that. Let's see here. Didn't realize the deadline came. So 4, 1, 2, 3. I'm gonna go ahead and remove all of chapter 4 till November 21st for now.
Thank you.